Assalamualaikum and good day. In this lecture video, we will look at the last subtopic of this chapter, which is catalytic kinetics. At the end of this lesson, you should be able to describe the two types of catalyst and catalysis. A catalyst is a substance that increases the rate of a reaction by lowering the activation energy. It does so by providing an alternative reaction pathway. The catalyst may react to form an intermediate with the reactant, but it is regenerated in a subsequent step, so it is not consumed in the reaction. A catalyst speeds up a reaction by providing a set of elementary steps with more favorable kinetics than those that exist in its absence. From this equation, we know that the rate constant, K, and hence the rate of a reaction depends on the frequency factor, A, and the activation energy, E subscript A. The larger A or the smaller E subscript A means the greater the rate. In many cases, a catalyst increases the rate by lowering the activation energy for the reaction. Let us assume that the following reaction has a certain rate constant K and an activation energy E subscript A. In the presence of a catalyst, however, the rate constant is Kc. It is called the catalytic rate constant. By the definition of a catalyst, rate of catalyzed reaction is greater than the rate of uncatalyzed reaction. These two figures show the potential energy profile for both reactions. Note that the total energies of the reactants A and B and those of the products C and D are unaffected by the catalyst. The only difference between the two is a lowering of the activation energy from E subscript A to E subscript A dash. Because the activation energy for the reverse reaction is also lowered, a catalyst enhances the rate of the reverse and forward reactions equally. This diagram shows the effect of a catalyst in a reaction. It compares the activation energy barriers of an uncatalyzed reaction and the same reaction with a catalyst. The catalyst lowers the energy barrier but does not affect the actual energies of the reactants or products. Although the reactants and products are the same in both cases, the reaction mechanism and rate laws are different in the catalyzed and uncatalyzed reaction. These are the main properties of a catalyst. It provides an alternative reaction pathway. It lowers the activation energy for both the forward and reverse reaction. It is usually chemically unchanged at the end of a reaction. The catalyst which decreases the reaction rate is called negative catalyst or inhibitor. Catalyst may react to form an intermediate with the reactants, but it is regenerated in a subsequent step, thus it is not consumed in the reaction. And catalyst usually has an optimum temperature. Only a small amount of catalyst is required for a reaction. There are two types of catalysts. Homogeneous catalyst, a catalyst that present in the same phase as the reacting substances. And heterogeneous catalyst is a catalyst that present in a different phase as the reaction substances. Catalysis is a process in which the rate and or the outcome of the reaction is influenced by the presence of a substance, which is the catalyst. There are three general types of catalysis depending on the nature of the rate increasing substance: heterogeneous catalysis, homogeneous catalysis, and enzyme catalysis. In heterogeneous catalysis, the reactants and the catalyst are in different phases. Usually, the catalyst is a solid and the reactants are either gases or liquids. Heterogeneous catalysis is by far the most important types of catalysis in industrial chemistry, especially the synthesis of many key chemicals. Here the list of 3 specific examples of heterogeneous catalysis that account for millions of tons of chemicals produced annually on an industrial scale. The Haber synthesis of ammonia, the manufacture of nitric acid via Oswald process, and catalytic converters. In homogeneous catalysis, the reactants and catalysts are dispersed in a single phase, usually liquid. Acid and base catalysis are the most important types of homogeneous catalysis in liquid solution. Homogeneous catalysis has several advantages over heterogeneous catalysis. For example, the reactions can often be carried out under atmospheric conditions, thus reducing production costs and minimizing the decomposition of products at high temperatures. In addition, homogeneous catalysts can be designed to function selectively for a particular types of reaction, and homogeneous catalysts cost less than the precious metal, for example platinum and gold, used in heterogeneous catalysis. Enzyme catalysis. Of all the intricate processes that have evolved in living systems, none is more striking or more essential than enzyme catalysis. Enzymes are biological catalysts. The amazing fact about enzymes is that not only can they increase the rate of biochemical reactions by factors ranging from 10 to the power of 6 to 10 to the power of 18, but they are also highly specific. An enzyme acts only on certain molecules that are called substrate, that is the reactants, while leaving the rest of the system unaffected. Enzyme catalysis is usually homogeneous because the substrates and enzyme are present in aqueous solution. An enzyme is typically a large protein molecule that contains one or more active sites where interactions with substrate takes place. These sites are structurally compatible with specific substrate molecules in much the same way as key fits a particular lock. In fact, the notion of rigid enzyme structure that binds only two molecules whose shape exactly matches that of the active site was the basis of an early theory of enzyme catalysis, the so-called lock and key theory, developed by the German chemist Emil Fischer in 1894. So these figures show the lock and key model of an enzyme specificity for substrate molecules. The figure below shows the binding of a glucose molecule in purple to hexokinase of an enzyme in the metabolic pathway. So see the figure from left to right. So you can note how the region of the active site closes around the glucose after binding. So frequently the geometries of both the substrates and the active site are altered to fit each other. The mathematical treatment of enzyme kinetics is quite complex, even when we know the basic steps involved in the reaction. A simplified scheme is given by the following elementary step, where E, S, and P represent enzyme, substrate, and product, and ES is the enzyme substrate intermediate. It is often assumed that the formation of ES and its decomposition back to enzyme and substrate molecules occur rapidly and that the rate determining step is the formation of product. In general, the rate of such a reaction is given by this equation. The concentration of the ES intermediate is itself proportional to the amount of the substrate present. And a plot of the rate versus the concentration of substrate typically yields a curve like this figure. Initially, the rate rises rapidly with increasing substrate concentration. However, above a certain concentration, all the active sites are occupied and the reaction becomes zero order in the substrate. In other words, the rate remains the same even though the substrate concentration increases. At and beyond this point, the rate of formation of product depends only on how fast the ES intermediate breaks down and not on the number of substrate molecules present.